Very good afternoon, all students. I hope you are doing well and now enjoying the subject algorithms and being more comfortable with the programming. I'm sure you must be feeling more temptations to implement and try whatever we discuss. So last class, we have discussed the backtracking algo, and due to exams pressure, maybe some of you might not have implemented, but I'll suggest you that all of you should implement first and then see. But here I'm sharing with you the sample solution for the n-queen problem so that when we discuss today, you feel better, comfortable nature of the backtracking logic. So as we discussed that, yes, we will have a main read number of queens and global array I'm taking for storing the results, where X will store the corresponding queen in Xi will store the corresponding queen in row I, and correspondingly for N, I will generate the result and display. So backtracking logic was divided into two modules. So I said for every kth queen, I will have the possible places in the kth row as 1 to n. And if the place is acceptable, the corresponding result will be saved. If the result is reaching to n, if k has reached to n, the result is ready. If I want multiple solutions, I can remove this exit. Otherwise, all solutions will be displayed. And if we have not reached to n, the recursion will be called. So in this recursion, the beauty is that automatically backtracking will make sure to go back and resume wherever it had previously gone. So if the answer is acceptable, current answer acceptable, we proceed further to recurse. If the answer is not acceptable, we backtrack to other answers for the same xk. If that is also not acceptable, reverse backtrack to go to the previous k, and it will all automatically happen by this particular function. Place logic, we are trying to check whether the kth queen can be placed at position xk or not. That means with the previous queens, I have to check the attack, and the attack will be checked either it is a corresponding vertical attack or it is the diagonal attack. So diagonal position I can say and return 0. If it is okay, return 1. Then finally queens I can display like this. So if I just execute it, let's say for queens 4, so I'll say for 4 queens, the corresponding answer is there. As I'm printing one answer only, so I am getting that. If I want multiple answers, accordingly I can remove that. Well, having said that, now let's resume and continue to discuss further in the same direction. So backtracking based, we have already discussed one logic, which was n-queen. And now today we will see some interesting programming, and you will be surprised as well as happy to see that the backtracking logic and implementation can be such a systematic and such a repetitive process that with a lot of programmings on backtracking, you will find a lot of similarity. Altogether different problems, but programming will become such a simplicity and as repetitive. For example, let's talk of some problem which is known as M coloring or graph coloring problem. That's another very interesting problem which has been shown to be very useful once the computers were invented. Earlier, it was a mathematical problem. And how did it all start? Effectively, let's say I have a map of India or map of world, and I want the map of India to be colored. So that obviously you must have seen in your school days a colored map. What was the reason of coloring? I'm sure you all have observed that aim was effectively to distinguish or clearly identify between different states. So effectively what was done? That the one state was colored in a different color than its adjacent states, so that the boundaries, etc., are visible. Yeah, similarly in the world map also, you could see continents colored different or countries differently colored. Well, if I say how many colors you have seen there used, so some of you will recall different colors. Count of the colors, probably you recall was something less than 10, maybe 5, 6, 7 colors used around that. Fine, it worked well. I was able to see how many minimum colors are needed to color. Can you find out that? How many minimum colors? So you will definitely say it is dependent on the map. What is dependent on the map? Can you tell me if I have a map available of India's map? So how many colors should be minimum needed? Will it be 7? Will it be 6? Will it be 9? What? So your answer, can you have some logic based on which it should be decided? Yes, some of you will say, as I discussed in the lecture, physical lecture, that you have an intuition, and probably that's a good logic to say that if a state, let's say I have state S1, and if a state one's, how many adjacents are there? So if I have a maximum adjacents known to me for any state, let's say some maximum adjacents to any states are 6. So then you will say probably 1 plus 6, 7 colors needed. Logic can be simple, that say S1 will be some color 1, and then it's all adjacents, they will have a different color. Logically sounds well, and they will have color, say 2, 3, 4, 5, 6, 7, some different colors. Total 6 different adjacents, 6 different colors. So maximum 7 colors should be sufficient. Or I'll say to be minimum 7 colors needed for coloring such graph or such map. Yeah, appears to be a good choice, could be well described. I think, yes, you have found a good solution. Such a intuition or such a logic is quite acceptable. I can say that was a greedy choice. Obviously, if it is a greedy choice, is it safe? Is it optimal? You have to prove that. Maybe you will give different logics. Maybe you will prove it. Yeah, appears to be good. But yes, that's why we always say that intuitions might not always work. I say probably it's not optimal. Not optimal. And I say the logic which you decided, ideally it is not the best logic to solve such problems. Reason, simple. Let's say this is state S1 and it has different adjacents. Let's say 6 adjacents. Adjacent 1, adjacent 2, adjacent 3, adjacent 4, adjacent 5, and adjacent 6. So what you thought was that if this state is given color 1, I will give this as a color 2, this as a color 3, color 4, color 5, color 6, color 7. So colors which you chose were 1 to 7. Appears to be fine, perfectly fine. This will definitely work, but this is not minimum. Reason, I could easily say, this is color 1, let this be colored 2, let this be colored 3, let this be again colored 2, let this be again colored 3, let this be again colored 2, let this be again colored 3. Only 3 colors needed here, and still all boundaries are distinguishable. So the logic which I greedy choice made was not the best logic, and I can easily see it's not a greedy choice or not a greedy algo. Greedy algo not suitable. So it's not a suitable problem for greedy algo, as a greedy choice I can easily see is not what really works in this case. If it doesn't work, then I'm not going to accept it in the way I am using it. So it's not the best choice. Well, then I can easily see the reason being that once I had 1, its adjacent was 2. Yes, a different color for 2 is okay. But 2's all adjacents also need to be known to me. Let me just shift this side. Let me just shift this also other side. Yeah, so that will be fine. So all adjacents of 2 also need to be known And then based on that, the colors will be further decided. Adjacents of 1 also have a choice. So I can see same logic will apply to the next adjacent 3, 4, etc. Effectively, it means all possible sequencing of these adjacents or permutations are to be explored. And based on that only, I can find the minimum requirement needed. Obviously, it becomes a backtracking problem suitable because I need all possible permutations, and as soon as some color becomes unsuitable, I will go back and do. So if I think backtracking, I have to always think of generate solution incrementally. Incrementally solution will mean I should aim to program in a way that somewhere x1 to xk is being generated, or I'll say x1 xi solution of x1 to I is ready, or I will say this is to be checked whether acceptable or not. If acceptable, then will mean go for recursively to I plus 1 onwards, find xi plus 1 recursively. If not, backtrack. Backtrack where? Backtrack firstly, give different value to current xi. If that will be attempted, if that also doesn't work, again try another value, another value. If all values exhausted, if they all get exhausted, obviously you have to backtrack. Further backtrack. Backtrack to xi minus 1 and explore with remaining values. So all this is effectively similar to what we have earlier done. So all this is, there was a connection break, so I'm just resuming. All this is similar to the n-queen logic, which we have already implemented. So just going further and then continuing with the same discussion, let me just change my page. And I think this will be, for the time being, put this side so that it doesn't disturb us. Fine. Yeah, so I said now how to make a solution. Let's assume M is known to me, and let's say 4. So I will store it as a globally. And I want to find out that can I solve this problem or not? So what use of computers have been in the past, that earlier mathematicians said that there are minimum 5 colors needed to solve such a coloring problem. And the target was that color a graph in a way that no two adjacent nodes or adjacent vertices have same color. So that is the target. And this was actually applied by mathematicians over the maps. And for years together, it was assumed that M is a 5 as minimum. Of course, when they applied over maps, the assumption was that each map is a planar graph. And mathematics says over a planar graph, M equal to 5 is minimum colors needed. What is a planar graph? I don't go in detail. Just it says that the edges won't cross each other if drawn on a plane, but I need not bother. My problem is simple, that what they said was that in correspondingly each map was made as an equivalent to a graph, where they said let's say each state will be correspondingly shown as a vertex. And if two states are adjacent or neighbors, then there is going to be an edge between them. Edge exists between them. For example, if I say Haryana is one state, so Haryana to Delhi, there is an edge available. Delhi is a different vertex. UP is another different vertex, and Haryana to UP, there is a border sharing. Haryana to Punjab, there is a border sharing. Haryana to Himachal, there is a border sharing. Haryana to Rajasthan, there is a border sharing. Maybe Rajasthan and Delhi also share. Delhi and UP also share. If UP and Punjab share, HP and Punjab share. If HP and Rajasthan share, accordingly, all those connections will exist. So ultimately, it becomes a graph coloring problem. And graph coloring with minimum colors, with minimum M. So once the computers were invented, mathematicians and maybe probably using backtracking logic, they proved that M equal to 4 can be the answer instead of 5. And they showed and proved that all planar graphs, they were able to be colored with 4 colors only. Of course, for that, they applied mathematics, algorithms, and all proofs, and computer was heavily used, and it was invented that instead of 5, 4 could be a good choice. How did they find? Obviously, they tried to color and make certain logics, and then proved or mathematically demonstrated. Well, how to do that? So let's go towards solution or logic. Logic is simple. I'll say, again, try to make incremental solution as it's appearing to be a backtracking problem. If it is a backtracking problem, I'll just have the backtracking problem solved in the similar manner by saying that let's start generating X solution as 1 to n total. That will be my final solution. So if I say, let's say there are colors, so I'll say color maybe, let's say, first vertex is given color 1, second vertex is given color 2, third vertex being given color 3, next vertex being given color 2, next vertex again 3, let's say fourth color to another vertex, color 2 again, color 3 again. So let's say if n was equal to 4 plus 4, 8, so I say this is color of vertex 1, and this is color of vertex 2, and this is color of vertex 8. Obviously, this means these two have to be different based on whether they were adjacent or not. 2 and 2 being the same means guaranteedly not adjacent, and all those choices have been taken. So my logic has to be now find color for each vertex. How to find? Obviously, I will say incrementally find. So what I'll say, maybe I'll say, let's choose for x1 some color, say M1, say first. This is obviously acceptable. So I will say x1 is ready. Find some color for x2. All possibilities to be explored. All possible colors could be given to it. And if it is acceptable, then I will say fine. Accept this as x1 to 2 ready. And then, so I'll say x1 is ready, x2 is ready. And then correspondingly add x3 and check whether it is okay or not. So some color given to x3. And let's say okay, then I will say x1 to x3 is already ready. Add x4 to it. And now check, is it okay or not? Say not, x4 color not acceptable for vertex 4. So this color was given, let's say color 2, and I find color 2 not acceptable. I'll say try with color 3. Still not acceptable, try with color 4. Not acceptable means all colors exhausted. x3 color should be changed and backtracking will be used. And let's say earlier this color was a 3. Now I'll give it color 4. Color 4 will mean further explore to giving x4 new color. And that is all recursive. So more or less the same process. So I will say, let's use global array for x. And each xi shows the color being assigned to vertex I. And if color is acceptable, till the current solution based on bounding function, I will say, I will store this color into xi. Otherwise, I will try with other color. Otherwise, I will back. If I have to do that, coding can be very simple. Let's say I will say void graph coloring or M color problem. Start with K and N. Of course, initial call I am assuming will be called obviously with 1N. K will be initially 1. So effectively now what I want to do, I have to assign color to vertex K. So what are the possible colors for K? I'll say the possible colors to this vertex can be any color from 1 to N based on some condition. So I'll say possible colors for kth vertex can be 1 to N or 1 to M to be precise, because maximum M colors are allowed. So I'm given that maximum M colors are to be used. Is there a possible coloring or not? So is possible coloring, is coloring possible with these M colors or not? That is what I have to find. So I'll say M is known to me, M is global, and I will be using this. If X, so I'll say now I have given a color, whether this color is acceptable or not. So I'll say, let's do all that programming into my place function. So kth vertex being given color xk, is it acceptable or not? If acceptable, I will say accept this answer, means xk will be given equal to this color selected. And if acceptable, now I have to go for the recursion. But recursion is never conditional, as we always know. So I'll first check if I have reached to final solution. Solution is ready. Nothing else to do. Print that answer or colors are ready. Else what? Else I have to recurse. Recurse to whom? Give a possible color to K plus first vertex. Now, having said that, just recall that this code is effectively more or less the same or similar to an queen function. And that was a generic module 1. So I say module 1 is primarily ensuring backtracking. If the color was not acceptable, obviously next color will be attempted. All colors attempted. If exhausted, backtrack to the same function for K minus 1. And that backtracking will be resumed and process automatically takes care. So everything happening automatically. So effectively this function is very similar. And now I have to make the function for corresponding place. Obviously the place function should return a true or false. So I will take it as int, and I'm trying whether xk color is acceptable to corresponding vertex k or not. How to check that? Obviously, this color, I will check whether this color is equivalent or it is, if this color is different from the adjacents or not. With whose adjacent? The currently decided colors. How many are decided? I know that I have effectively decided up to k minus 1. So if this is not adjacent to then any of them, obviously it can be given any color and color is acceptable, but it should not have same color as its adjacent ahead. Which are the possible vertices which have been already covered? I know they are up to k minus 1. So I can say j equal to 1 to k minus 1. I have to repeat. What I have to do? Check whether corresponding selected vertex, that is xj vertex versus vertex k. Vertex K is being discussed now. If they are not adjacent, not an issue. If they are adjacent, the color has to be checked. So what I'll say, if they are adjacent or not, how to check that? I need the graph. So I'll say I have to do some condition, and let's assume I have the adjacency matrix available to me. So whether these two are adjacent or not, if they are adjacent, then what? Then their color should not be same. So if they are adjacent and the corresponding color is the same, how to do that? Color effectively, xj is the color of the corresponding. So I'll say vertex was, to be precise, jth vertex, not xj. Jth vertex versus vertex k, I have to see. Color of the jth vertex, I have given xj, and color of the kth vertex is being considered xk. So if this color is the same, what does that mean? Effectively, it means return 0, return false, because color is not acceptable. So I will be returning 0. And if color is acceptable, or if they are not adjacent, nothing to bother. If they are adjacent and color is different, still nothing to bother. Repeat this process for all j's, and if you are able to find, you are able to return 1 that this color is acceptable. Now again, compare this code with nqueen logic, with M2 module of nqueen. You will find a lot of similarity. So that's the beauty. Effectively, the only change being here. So changed here, and this change is only because of the corresponding bounding function. And the corresponding bounding function will be accordingly coded, and I'm effectively ready. Having said that, now just understand what a beauty of the corresponding algorithms of the backtracking is, that nqueen versus M coloring were altogether different problems, and still my problem solution using backtracking is very similar. So what we always say, that first module which I am designing is module M1, primarily the backtracking and recursion. And that will be mostly common with all modules or all problems. M2 will have the bounding function characteristics, and that also will be in a similar manner processed except conditions. So only the condition to be checked will be different. The process or logic will be quite similar. So only the conditions on basis of which decision will be made, those conditions could be different. So programming becomes such a fantastic way of solving that the same problem got solved without much of an issue. Not only that, just going beyond this, if you see, we will see another problem, which is again a different kind of a problem, which is called as a Hamiltonian cycle problem. That's again another totally different problem, but you will be surprised to see that the solution to this will also come in a very parallel and similar manner. And that's the beauty of today's discussion, that recursion and backtracking, such a simple way of implementing such a simple and systematic process that all exponential processes get easily solved. And even if you have exponential permutations, all that can be systematically solved without much of a problem. Talking of Hamiltonian cycle problem, we should know that it's again from a graph and graph-based problem. In that, we are supposed to find whether a graph has Hamiltonian cycle or not. What is Hamiltonian cycle? So I should know what is a Hamiltonian cycle. So I say it is a round trip over the graph say if graph has, let's say, n vertices, so I'll say it's a round trip over the graph along all edges along the available edges, whatever edges are there could be any number of edges, but what should be that? So that or such that correspondingly every vertex is visited exactly once only, exactly once, and because I am using the word cycle, it means I return back to the starting vertex. So this is what is called as a Hamiltonian cycle. For example, if I have a graph of, let's say, n vertices, let's assume that I have graph. So I need to just shift this side and have this. Yeah. So let's assume n equal to 7. Then I can say I need a cycle. Hamiltonian cycle means all vertices will be covered. Let's say I started from 1. Maybe I say a cycle is 1, 5, 3, 7, 2, 6, 4. So all 7 vertices covered. It means that the corresponding iteration or a trip will mean from vertex 1, I will go to 5. So this edge guaranteedly exists. Then 5 to 3, I will go. Then 3 to 7, I'll go. 7 to 2, I'll go. 2 to 6, I'll go. 6 to 4, I will go. And then from 4, to make it as a cycle, I'm able to go back to 1. So Hamiltonian path means all vertices covered once and exactly once, but cycle means going back also. So it's a loop. For example, if you wanted to visit different cities of the country, you have a wish list, you wanted 5, 7 cities to be covered. So you decided cities, but you should choose a route in a way that you don't repeat a city again. That means there must be an edge available from city A to B if you plan in that sequence. So you have to identify sequence. So find such sequence if the cycle exists. And if cycle doesn't exist, obviously it won't happen. So I want this solution. Obviously now this solution is dependent that if I, let's say from 1, should I go to vertex 5 or not, will depend whether from 5, will I be able to traverse in a way that all vertices will be possible to be covered. Is that possible or not? So if possible, obviously this will be a good choice, but I can't say tell at this. So maybe I'll say from 1 to 5 decide because there was an edge. But from 5, I will again decide another edge. And as soon as I find, let's say I went from 1 to 5, I decided. From 5, I went to 3. From 3, I went to 2. And then I found from 2, I'm not able to go to any other new vertex. I can go only to 3. I can't really use that. I can go to 5. I can't use that. I can go to 1 because these are the only edges available. That means coming to 2 was a wrong choice. So I'll go back. From 3, I will say, choose another vertex. Let's say you chose a 7. Then you will say, from 7, can I find another new vertex to which I can go? And like this. So again, you can say, this all depends on all permutations because correspondingly edges should be available and cycles should exist. So again, it's kind of a permutation exploration problem and backtracking can be one of the way to solve. If I want to solve using backtracking, I have to think of deciding the solution incrementally. So obviously, I will say first thing. In this case, I can always choose a starting vertex. I can freeze the chart starting vertex without any problem. Let's assume this is 1. And without any loss of a generality, I can claim that starting vertex can be freezed. Obviously, because 1 will guaranteedly appear in the cycle. And it's a cycle, anyone can be in the starting vertex. Because every vertex has to be in a cycle. It's a cycle like this. So if I have, let's say, a cycle going 1, 3, 5, 7, 2, and then 6, 4. Now, anyone can be a starting vertex. You start from here, still you will be able to find a cycle and like that. So effectively, this means that you can always have a cycle without much of a problem, and anyone can be taken as a starting vertex. So I chose this, and this can be perfectly fine. If cycle exists, guaranteedly I will be able to find an answer this. Whether I chose 5 as a starting, still it will be possible. So without loss of generality, I can say freeze anyone as a starting vertex so that from there, different adjacents and decisions can be made. Having said that, now I can easily say, once I know this, the things are simple. Again, how to solve? Solution or logic? Again, always try incremental solution. So decide a solution from x1 to xk. So x1 to xk means all these are accepted up to k minus 1, and this is being attempted. And if acceptable, either you will go for recursion to k plus 1 or backtrack. So I should design my solution in a way. How to do that? I will say, fine, I have already chosen x1 to be, just 1 second. So I have chosen x1 to be 1, and this becomes one freezed choice. So I will say, with this, I will decide starting vertex is this. Now, so x2 will mean which can be the next vertex to be traversed, to be visited. Find such vertex. Of course, this vertex will be dependent on the adjacents. So I'll say, what are the all possible values? Consider all permutations, and then I'll find whether it is acceptable or not, and accordingly proceed. And then based on that, if found, then I will say x1, x2 solution ready. Try the same for x3. So find vertex 3 to be traversed. For example, in the last case, I will say my x1 to 7 answer will be nothing but I will generate answer 1, 5, 3, 7, 2, 6, 4. This means my first vertex is 1. Second vertex to be visited is this. That means this is a value x2. Second vertex in the Hamiltonian cycle. And this becomes 7th vertex in the cycle. So effectively, this will become the value for x7. This means every time I have to choose xi, choose a vertex at ith step. Which one will be this vertex? Obviously, not covered already, one thing. And secondly, the path or edge is still feasible. And if it is last, obviously cycle is still feasible. Well, all this part of this logic, we have to again implement. So solution can be again simple. I can proceed without much of a difficulty. And I say, well, if I want to just solve this in this particular manner, I will say, I will do nothing special, but just start in the same way. I'll say void correspondingly Hamiltonian cycle function to be implemented with k and n. The only difference being initial call will be with k equal to 2 and xk is 1. That is 2n will be call made, and before this x1 is guaranteedly starting vertex. Although I can choose this also to be anyone, but why to unnecessarily waste when it is guaranteed to be a part of answer? So now this. Then, now I am supposed to give kth step some vertex to be chosen. So again, choose the possible values or assign a possible value for second vertex at step K. What are the possible vertices which can be covered at step 2 or at step K? Obviously, any vertex out of 1 to n. So I can say still it is for xk equal to 1 to n. I have to effectively try giving this vertex number. So what presently decided is that I am giving at step K the vertex number xk to be chosen. If it is acceptable, I will say fine, proceed further. Proceed further means what? This means currently selected vertex or xk vertex is acceptable as kth vertex is selected. And if acceptable, if k equal to n, accordingly I know solution ready. Else, recursion needed. All remaining similar. If you see again, the whole process remains the same. If not acceptable, try the next vertex. Whether this is allowed or not, all logic will go to the place. So the problem specific logics will be implemented in the place function, and this becomes general. If not acceptable, if nothing exhausted, I'll be going to the recursion or backtrack to the previous, everything same. So effectively, code is still same. Just see, entirely different problem, but still same logic for your recursion oblique backtracking. And all code works without much of a difficulty. Then comes, now I have to think of the solution corresponding to the corresponding place function. So place function I have to decide. Now here, what is the logic? I said currently x1 to xk is being attempted and acceptable or not. What does that mean? x1 to xk minus 1 vertices have been already accepted. I have to check whether xk minus 1 are already accepted and whether xk is acceptable or not. What does that mean? For example, I say I have already decided 1, 5, 3, 7 to be the path and k equal to 5. So I'm saying fifth vertex, which one should be chosen? Let's say I'm trying to give it value 2. Now that will decide whether 2 is acceptable or not. What are the checks to be made for 2? 1, 5, 3, 7 means 1 to 5, 5 to 3, 3 to 7, perfect, and they were all distinguished. Whether 2 is acceptable or not first depends. Am I having a connection or edge between 7 to 2 or not? If not, obviously 2 cannot be acceptable. I have to try other value. If acceptable, probably this becomes a good choice. And based on that, I can accordingly say that more or less I am ready with the place function. So I will say int place k and xk being attempted. What I will say? First thing, whatever xk I have chosen, is it acceptable to be part of this path? Depends whether previously selected vertex versus current vertex, there is an edge or not. So is there an edge? From where? From previously selected, just previously selected vertex to the current vertex which we have decided. If yes, means perfect, this value is acceptable. But if not, I can say I have to decide. So is this acceptable? Maybe yes. Should I return 1? I will say not probably. I will reverse it. Why? I'll just understand. If not edge present, I can guaranteedly say return false, because this answer is not accepted. But if yes, then what should I do? I could say edge exists, but still it might not be acceptable. Why not? Just think. Probably I might be repeating the vertex number. Say vertex 1 I am trying here. current xk is 1, 3 or vertex 7, 1 edge exists. So 7, 1 vertex is still okay, or 7, 1 edge is still okay, but 1 is not correct vertex to be attempted because 1 is already traversed. That is also a condition in Hamiltonian cycle. So if yes, that will mean I have to check whether it is already visited or not. How to check? Obviously, I will need a loop. Up to k minus 1 decisions have been made. So I can say from j is equal to 1 to x minus n is, I'll check, is xk equal to already visited? That effectively means xj. If yes, again, I will say return false because this is not acceptable. And if I come out of the loop, probably I can say it is unvisited. So kth vertex is unvisited, and or I'll say xk is unvisited. It can be accepted. More or less, probably I think I can return 1. But should I return 1 immediately or not? I have to now decide. So the only catch here being at all these stages, I have checked everything except the cycle. How to check for the cycle? For the cycle effectively mean corresponding to the last vertex. Let's say I have 1, 5, 3, 7, 2, 6, 4. But once I reach to 4, I have to ensure that edge 4, 1 should exist. Only then the cycle was guaranteed. And this was never checked anywhere else. Once I reached to k equal to n, I said print the answer. Cycle was never attempted because the path was attempted. I checked for 6, 4, and that's it. That code can be either placed here, but I will not prefer to place here because I want all bounding function and conditions to be here. So that I should check here. If k equal to n, that means I have reached to the last vertex being selected, and that is unvisited. I will write it was unvisited and acceptable, and now this should be selected. But if it is last vertex from xk, that is, it is equivalent to xn, to x1, edge existence must be checked, and accordingly the decision will be made. So that becomes a simple logic. So if you again see, the logic is simple. This is more or less similar already. Earlier also we have done the same coding. So the only thing was this additional check and maybe something like this additional check. Rest code remaining very similar. Code is otherwise similar to what we have already done. And if you see the beauty of this, all coding becoming very similar to module M2 of N Queen or corresponding M color. So still I can say more or less the same. And bounding function characteristics being coded here. So those who are comfortable now in coding must try yourself and attempt to complete this. Rest, those who are not comfortable, for them, I will show the partial code to this problem, and correspondingly, there will be a more easiness for you to implement at your own level. So I'll just say, let's go back and see into the corresponding partial code into the dev CPP. I'll say M coloring problem. First of all, I'll have a main. I will be reading a graph. In the reading graph, you can have the corresponding adjacency matrix read. Once you read the matrix, correspondingly, that will be stored into some graph. Graph I have taken as a 2D array. So I am taking graph declared into this main as max. Maybe I have declared 50, 30, whatever. And in that read graph, effectively, I ask the adjacents, and based the adjacents, the corresponding adjacency matrix is accordingly updated, and I make 1 or 0 correspondingly. So you read either way. You have already done programming over adjacency matrix. You can easily see that. I want to check the display of the graph. The parameter passing, you have to be careful that this parameter or this boundary or this size is must. Ideally, here also you should pass, like earlier I have done, but you have a choice. Read, and then finally comes to my logic, M coloring logic. So M coloring logic, pass the parameters. Of course, now you should know that which parameter or which size is must. I have defined max as a 20, so it will be permanently used there. All M colors being attempted, whether color is acceptable or not, this code, easy, otherwise recursion. Place logic, effectively, probably you need a loop here, and out of already selected vertices, you will check if current vertex k is adjacent to any one of them, then that is going to be, or I'll say that is going to be checked. So kth vertex, and it is being given color xk. So whether xk color is the same to any vertex which is adjacent. If so, return 0, otherwise return 1. That much code should be sufficient to you to attempt. If the vertex is not adjacent, any color is okay. So if the vertex is adjacent and has same color, I'm supposed to return 0. If no adjacent is found to have same color, obviously return 1. And then accordingly, you can have very similar coding for the Hamiltonian cycle. If you see this code remaining exactly same as in N queen or in the M color. Then comes placing of the logic. So place function, first of all, I'll check, is there any edge? Is there no edge between the last visited vertex to the current? Return 0, because that is not acceptable. Then I have to check if the vertex is already visited or not. So there are many visited vertices. Correspondingly, some loop needed here. If the visited vertex is already being repeated, return 0. If k is less than n, means the cycle was not to be checked at present, value is acceptable, and everything is perfect. I can return something here. If the value is equal to n, if there is the path becoming the cycle or not, that will be checked whether there is an edge from the nth selected vertex, that means effectively xk value, to the first vertex, that means x square 1. If yes, accordingly, I will say this is acceptable, otherwise it is not acceptable. So in the main, I can accordingly declare graph, read graph, and then call Hamiltonian cycle, starting with the 2 and x1 taken as 1. So with this can be one of the excellent. So the final remarks. Now I can easily see that my programming with backtracking is such a simple, and we have effectively divided my whole logic always into 2 modules, where I have module M1, which takes care of a general backtracking and recursion logic, and bounding function or problem-specific characteristics in module M2. In Horowitz, this topic you need to read from, not in Corman. So Corman doesn't have the detailed explanation of this. These are unsolved problems given there. For detailed study, you should read the book of Horowitz and Sahni on algorithms. And this, the book which you should read, is having 1 chapter of backtracking, and the book is not the data structure book. Book title is Algorithms book. From that book only you must read this topic. And the only thing why I'm suggesting you is that in book M color and Hamiltonian cycle, these codes given in the book have slight different, in the context that the only change being the possible values which are to be given to xk, they are also being given in the module M2 to kth answer or 2xk, these are being given in M2. On the other hand, what we have done was all this we have done in M1. In N queen, we did the way exactly parallel or similar logic we have discussed. So that is one and the same thing. Both are equivalent. You can do any one. The purpose of telling you is that you should attempt any one as per your choice, but don't get confused by reading in the book that how the code is different. What I mean is that while discussing in the book, if you see, you will find the only one change in the sense that this whole logic where I have given correspondingly, this was xk, so I'll say this was a for loop to be precise. There was a mistake. This was a for loop. When I talked of M coloring, I'm sorry, this should have been for. So for loop, which I have used this one in the book, this code or this is shifted to module M2. M2 means downwards. One and the same thing. Similarly, the same concept being used in the Hamiltonian also, where I had used this code to have for loop in the Hamiltonian also, this function had used these all possible values. This also effectively has been shifted into module M2 to this module. That is the only change, but if you are not understanding this, need not bother. I just wanted to share so that you don't get confused while reading it from the book. So nothing to worry, and effectively that will work in the simplest possible manner. So having said that, I think I will wind up here and stop my lecture. So bye-bye and all the best to all of you.